Welcome to the Unsupervised Learning Playbook. In the world of machine learning, we often talk about supervised tasks, feeding a model labeled data to train it for specific predictions. But what happens when the data doesn't come neatly labeled? What if you have petabytes of information, but no human has ever gone through and categorized it? That's the challenge and the immense opportunity we address today. Unsupervised learning is fundamentally about finding structure in a world without labels. It's about letting the algorithm explore the inherent patterns, clusters, and anomalies hidden within the raw data itself. Unsupervised learning forms the backbone of foundational AI systems, allowing models to learn useful representations and general knowledge about the world without explicit human guidance. Over the next few minutes, we will dive deep into the core concepts, explore the most crucial algorithms like k-means and DBSCAN, and understand how these tools can unlock massive value from your unlabeled datasets. Let's begin our journey into discovering the silent intelligence hidden within the data. To set the stage, let's look at one of the most famous analogies in machine learning, courtesy of Turing Award winner and chief AI scientist at Meta, Yann LeCun. He famously said, "If intelligence was a cake, unsupervised learning would be the cake, supervised learning would be the icing on the cake, and reinforcement learning would be the cherry on the cake." This quote beautifully encapsulates the foundational role of unsupervised learning. Think about it. The cake, the actual substance and structure, represents unsupervised learning. It involves learning fundamental representations and hidden patterns directly from raw, unlabeled data, providing the essential knowledge base. The icing, supervised learning, is built on top of this foundation. It's about leveraging labeled data with known outcomes for specific tasks, much like a teacher guiding a student. And finally, the cherry on top is reinforcement learning, learning through trial and error, receiving rewards or penalties to maximize a goal. The takeaway here is crucial. For a machine to achieve true, generalized intelligence, it needs that robust foundational understanding that only unsupervised methods can provide. Why is unsupervised learning so critical today? Because of the sheer volume of unlabeled data we generate every second. The vast majority of data available in the world, images, text logs, sensor readings, comes without any neat labels. Consider the example shown here, a modern manufacturing line generating thousands of product photos daily, like these gears and bearings. To use a traditional supervised classifier to detect defects, human experts would have to painstakingly and manually label every single image as normal or defective. This process is inherently slow, incredibly costly, and tedious, often taking weeks or months to build a usable dataset, and it becomes a massive bottleneck when data volumes scale up. Unsupervised learning offers a powerful solution, a way to exploit this massive, untapped trove of unlabeled data directly. Instead of teaching the model what a defect is, which requires labels, we let the model learn what normal looks like by observing thousands of instances, and then flag anything that deviates significantly. This allows us to find structure and derive value without paying the labeling tax. Unsupervised learning isn't just one monolithic concept, it encompasses several major tasks designed to extract different types of structure. We're going to focus primarily on the three most common and impactful applications. First, we have clustering. This is the process of grouping similar instances together into clusters based purely on their inherent characteristics. It's a workhorse for data analysis, essential for tasks like market segmentation, breaking down complex data into meaningful groups, and even image segmentation where pixels are grouped by color or texture. Second, we look at anomaly detection. This is a powerful task where the model learns the characteristics of normal data and flags any instances that deviate significantly, the outliers. It's vital in real-world scenarios like financial fraud detection, where finding a few unusual transactions among millions of normal ones can save huge sums, or identifying defective components on an assembly line. Finally, we have density estimation, which involves estimating the probability density function, PDF, of the process that generated the data. This helps us understand exactly how the data is distributed in feature space and is often used as a precursor for more advanced analysis or for implementing robust, mathematically sound anomaly detection systems. Understanding these three tasks is key to mastering unsupervised techniques. Before diving into algorithms, let's clearly distinguish the most common task in supervised learning, classification, from its unsupervised counterpart, clustering. Look at the left diagram, classification with labels. Here, the data points are already pre-categorized and labeled by shape, circles, squares, and triangles. We train the supervised model to learn the specific mapping between the features of these points and their predefined class labels. We use these labels as ground truth to guide the learning process. Now look at the right diagram, clustering without labels. All the points look the same, they are just dots. The data is entirely unlabeled. The task here is fundamentally different and much more challenging. It is an unsupervised task where the algorithm must autonomously discover the inherent groupings in the data, purely based on proximity and similarity, without any external guidance or feedback. The goal is to partition the data into distinct, meaningful groups solely by observing their positions relative to each other in feature space, requiring the algorithm to infer the latent structure itself. If there is one algorithm that is the undisputed workhorse of clustering, it is k-means. K-means is a simple, highly efficient, and globally popular algorithm designed to find a predefined number of clusters. Denoted by the parameter k, the core mechanism works by iteratively identifying k cluster centers, known as centroids, and then assigning every data instance to the nearest one. This process attempts to minimize the distance between data points and their corresponding cluster centers. The key idea illustrated in the lower left is its reliance on a Voronoi tessellation. This is a partitioning of the data space into distinct regions, such that every region belongs exclusively to a single centroid. All points within that region are mathematically guaranteed to be closer to that centroid than to any other. K-means is fast, easy to implement, and often the crucial baseline algorithm data scientists reach for first due to its computational efficiency, especially with very large datasets. K-means is an elegant iterative process that alternates between two steps until the cluster centers stabilize. Let's walk through the 4 key stages. Step 1. Initialize centroids. We start by selecting k initial data points to act as our first centroids, often selected randomly, marked by the x's. Step 2. Assign instances, the assignment step. In this step, the algorithm calculates the distance from every single data point to all k centroids and assigns each instance to the closest one. This forms our initial, rough clusters. Step 3. Update centroids, the update step. Once all points are assigned, the centroids are adjusted. Each centroid is recalculated as the mean, the geometric center, of all the instances currently assigned to its cluster. This movement minimizes the within-cluster variance. Step 4. Converged. We repeat steps 2 and 3 iteratively until the centroids stop moving significantly, which indicates that the algorithm has converged to a stable solution. A crucial mathematical note is that k-means is guaranteed to converge, as the mean squared distance between instances and their closest centroid, a critical metric known as inertia, can only decrease at each iterative step, ensuring that the solution always improves or stabilizes. While k-means is guaranteed to converge, it only guarantees convergence to a local optimum, not necessarily the global optimum. This dramatic difference is illustrated here and defines the peril of bad initialization. The quality of the final clustering solution depends heavily on the initial placement of those k centroids. Look at the 3 outcomes. Suboptimal solution 1, where the initial centers were placed poorly, resulted in an inertia of 600.4, indicating very loose, poorly defined clusters. Suboptimal solution 2 is better, achieving 219.6. However, the optimal solution achieves the lowest score, 211.6. To quantify the quality of these solutions, we introduce the crucial metric, inertia. Inertia is defined as the sum of the squared distances between each data instance and the centroid of the cluster it belongs to. Our objective in k-means is always to find the solution that minimizes inertia. Since random starts can easily land us in suboptimal local minima, we must use smarter techniques to ensure better initialization, which we'll discuss next. The proven solution to the problematic random initialization in k-means is k-means++. This is an improved initialization algorithm that dramatically increases the likelihood of finding a globally optimal or near-optimal clustering solution. Instead of selecting centroids purely at random, k-means++ uses a smarter, deterministic approach designed to select centroids that are maximally distant from one another, ensuring good initial dispersion. Here's how it works. First, one centroid is chosen uniformly at random. This is our starting point, C1. Then, for every subsequent centroid, we choose a remaining data point with a probability proportional to the squared distance from that point to its closest existing centroid. As you can see in the visualization, potential cluster centers that are far away from existing centers have a much higher probability of being selected. This intentional separation ensures that the initial cluster centers are well dispersed across the data space, leading to a much better final clustering result and a significantly lower inertia score compared to purely random initialization. This method is so effective and reliable that it is the default initialization method used in scikit-learn and other major machine learning libraries. A critical challenge in k-means is deciding on the value of k, the number of clusters, since the algorithm requires this hyperparameter upfront. If we choose the wrong k, the results will be misleading. We rely on two primary heuristics to find the optimal number of clusters. Method 1 is the elbow method, which uses the inertia metric we discussed. We plot inertia as a function of k. Inertia will always decrease as k increases, because adding more centroids naturally means every data point is closer to its assigned center. However, we look for a distinct point on the curve, the elbow, where the rate of decrease sharply changes. Past this elbow, the marginal gains in reducing inertia are minimal, suggesting that additional clusters are just overfitting or segmenting too finely without adding true structural value. It's a useful, though often coarse and subjective, heuristic. Method 2 is the silhouette score, which is generally considered a more robust approach. The silhouette score measures how similar an instance is to its own cluster compared to other clusters. It ranges from -1 to +1. Scores closer to +1 indicate dense, well-separated clusters, while scores near 0 or negative indicate overlapping or misassigned points. We choose the k that yields the highest average silhouette score, offering a more objective and mathematically principled way to select our cluster count. While the single silhouette score average is a good starting point, the silhouette diagram offers a powerful visualization that provides a much deeper look into the internal quality of the clustering solution. This diagram plots the silhouette coefficient for every single instance in your dataset, grouped visually by cluster. Let's break down the components. The height of each silhouette shape tells us the number of instances within that specific cluster. The width of the shape represents the actual silhouette coefficient for those instances. Wider shapes, meaning coefficients closer to +1, are always better. The dashed line indicates the mean silhouette score for all instances across the entire dataset. The real insight comes from analyzing the uniformity and shape of these silhouettes. Clusters with narrow shapes, or many points falling to the left of the mean score, are considered poor quality. By comparing diagrams for different values of k, say k equals 4 versus k equals 5, we can visually determine which choice yields clusters of more uniform size and quality, helping us avoid solutions where one cluster is perfectly defined, but others are messy. This visualization provides essential diagnostic power beyond a simple single average score. While k-means is fast and effective, it's essential to understand its inherent limitations, which stem from its core mathematical assumptions. The fundamental problem is that k-means operates by finding the mean center and drawing boundaries equidistantly between centers. Consequently, it assumes clusters are spherical, roughly equal in size, and possess similar density. When the underlying data structure violates these assumptions, k-means struggles dramatically. Take the visualization on the left. These three distinct, elongated or non-convex clusters are clear to the human eye, but k-means would fail to separate them cleanly because it wants to draw circles or spheres around the centroids. The key limitations are clear. It fails on clusters with non-spherical shapes. It performs poorly when clusters have highly varying sizes, often partitioning the largest cluster into pieces, and it is highly sensitive to clusters of different densities. This means k-means is great for well-separated blobs, but often inadequate for complex, real-world data distributions. As a crucial pro tip, always scale your input features before running k-means. While scaling won't fix structural flaws, it generally helps the algorithm by making cluster distributions more uniform in feature space, improving results significantly. Let's look at a concrete, highly visual application of k-means clustering: image segmentation. The task here is to partition an image into multiple meaningful regions or segments, specifically based on color. In this process, we treat every single pixel's RGB value, its red, green, and blue components, as a distinct data point in a three-dimensional feature space. We then execute a simple three-step process. First, we treat each pixel's RGB value as a data point. Second, we run k-means to find k-representative colors, which are the cluster centroids in this 3D color space. Finally, we replace each pixel's original color with the color of the centroid it belongs to. This effectively simplifies the image's color palette to just k colors. Observe the results with varying k with k equals 2, the image is reduced drastically. As we increase k to 4 and 8, more details are captured. However, note the key observation. With a low k, the small but distinct red color of the ladybug gets merged with the surrounding green or brown colors. This happens because k-means prefers clusters of similar sizes. If the red pixels are too few, they are mathematically merged into a larger, nearby cluster, highlighting a practical limitation of k-means when trying to segment small, detailed, but important objects. One of the most powerful uses of unsupervised learning is in semi-supervised learning, where we leverage unlabeled data to dramatically boost the performance of a supervised model. Consider this common challenge. We need to train a handwritten digit classifier, but can only afford to label a tiny subset, 50 examples out of 1,400. Our initial baseline logistic regression model, trained on those 50 random labeled instances, achieves a modest 75.8% accuracy. We can improve this drastically using k-means clustering in 4 steps. Step 2, smart labeling. We cluster the entire 1,400 image dataset into 50 clusters. We then only label the single most representative image, the one closest to the centroid, from each cluster. Training on these 50 smartly selected, representative labels immediately boosts accuracy to 83.4%. Step 3, label propagation. Since the data points within a cluster are similar, we propagate the representative images label to all other instances in that same cluster. Training on this now fully, but automatically, labeled dataset pushes the accuracy up to 86.9%. Step 4, outlier removal. We go one step further and discard the 50% of instances in each cluster that are farthest from the centroid, treating them as low confidence or noisy examples. This final step pushes our accuracy to a remarkable 88.4%. By leveraging k-means to structure the unlabeled data, we achieved a significant performance boost from 75.8% to 88.4% without requiring thousands of costly human labels, showcasing the incredible efficiency of semi-supervised techniques. The pursuit of efficiency in labeling leads us directly to active learning, a human-in-the-loop approach. Active learning is a robust, cost-effective strategy where the algorithm intelligently interacts with a human expert, requesting labels only for the most valuable, informative data points, thus maximizing the return on investment for labeling effort. The process operates in a continuous cycle, shown in the diagram. We first train the model on the currently available labeled data. Then, we use the model to make predictions on all the remaining unlabeled data. Critically, the model then employs a strategy like uncertainty sampling to find the most uncertain instances. These are the points where the model is least confident in its own prediction, often measured by the lowest prediction probability or high entropy. These most difficult, highest value instances are then presented to the human expert, who provides labels. These new, high-value labels are then added to the training set, and the cycle repeats. This strategy ensures that we are not wasting time labeling easy or redundant data points, but rather efficiently guiding the model's learning by targeting its precise knowledge gaps, dramatically reducing the overall data required to achieve high performance. We previously established that k-means struggles severely with non-spherical shapes. To handle complex structures, we turn to a fundamentally different approach: DBSCAN, or density-based spatial clustering of applications with noise. Its core idea is that it defines clusters as continuous regions of high density, allowing it to find clusters of any arbitrary shape, perfectly fitting those elongated structures that defeated k-means. DBSCAN relies on three key concepts. First, the epsilon neighborhood. Epsilon neighborhood is the region within a small distance epsilon of any given instance. Second, a core instance is a data point that has at least min samples neighbors within its epsilon neighborhood, meaning it sits in a dense area. Clusters are formed by chaining together these core instances and their reachable neighbors. Finally, a significant advantage of DBSCAN is its inherent robustness to noise. Instances that are not core points and not in the neighborhood of a core point are labeled as anomalies or noise, typically assigned the label -1. As seen in the Moon's dataset visualization, DBSCAN successfully separates the two intertwining, crescent-shaped clusters while automatically identifying scattered noise points, the X's. DBSCAN offers distinct advantages and disadvantages compared to k-means, which are important to consider for deployment. Let's look at the pros first. Crucially, DBSCAN does not require you to specify the number of clusters, k, beforehand. It discovers the number of clusters automatically based on the density of the data. Secondly, it is excellent at finding arbitrarily shaped clusters, which k-means cannot handle effectively. And third, it is inherently robust to outliers because it automatically identifies points in low-density areas as noise, labeling them as -1, rather than forcing them into an existing cluster. However, DBSCAN also has significant cons. It struggles when clusters have significantly varying densities. If one cluster is very dense and another is sparse, setting a single epsilon dollar and min samples threshold that works for both becomes impossible. Furthermore, its performance is highly sensitive to the chosen eps and min samples hyperparameters, requiring careful and often costly manual tuning. Most importantly, DBSCAN's computational complexity is roughly O(m)2, where m is the number of instances. This quadratic relationship means it does not scale well to large datasets containing millions of data points, often making it impractical for big data applications, unlike the linear complexity of k-means. Moving beyond distance-based clustering, let's explore the powerful probabilistic approach embodied by Gaussian mixture models, or GMMs. If k-means assumes spherical clusters and DBSCAN finds arbitrary shapes, GMMs are the right tool for clusters with more flexible, ellipsoidal shapes. This ability to model non-spherical clusters that are still geometrically well-defined makes GMMs highly versatile. The core idea behind GMM is fundamentally probabilistic. It is a generative model that assumes the observed data was generated from a mixture of several underlying Gaussian, or normal, distributions. The parameters of these distributions, the mean, the covariance matrix defining the shape and orientation, and the weight of each component, are unknown. The model's job is to infer these parameters. This inference is achieved through an iterative optimization technique called the expectation maximization (M) algorithm. The M algorithm finds the best fit for the parameters, assigning instances probabilistically to clusters rather than using the rigid, hard assignment of k-means, allowing for more nuanced data modeling. GMMs are prized because they offer capabilities that extend significantly beyond basic clustering, particularly in the realm of soft assignment and anomaly detection. First, they perform soft assignments. Unlike k-means, which performs hard assignment by forcing a point into a single cluster, a GMM provides a probability that each instance belongs to each cluster. This richer probabilistic information reflects the natural overlap and ambiguity often present in real-world data. Second, GMMs are powerful density estimation tools because they are generative models. Once trained, you can use the model to estimate the probability density at any given location in the feature space using the score samples method. This capability is perfect for anomaly detection. Instances located in low-density regions, the areas where the model believes the probability of generating that data is very low, are likely anomalies. As you can see, the stars far from the Gaussian ellipses are marked as anomalies. You can define a density threshold. For example, flag the 2% of instances with the lowest density scores to robustly and mathematically identify outliers in your dataset. Choosing the number of components K for GMMs presents a challenge because simple heuristics like the elbow method or the silhouette score, which are optimized for dense, spherical k-means clusters, often fail to give reliable results for GMM's non-spherical components. Therefore, we adopt a principled approach rooted in statistical theory using information criteria that rigorously balance model fit with model complexity. The two main criteria are the Bayesian Information Criterion, BIC, and the Ackic Information Criterion, AIC. The fundamental goal is to choose the number of clusters K that minimizes the BIC or AIC score. These criteria introduce a heavy penalty term for models with more parameters, meaning more clusters or overly complex covariance matrices, and simultaneously reward models that fit the data well. We are looking for the sweet spot that minimizes this score, as illustrated in the graph, giving us a statistically robust and objective way to select the optimal number of components for our probabilistic mixture model, ensuring we choose the simplest model that adequately explains the data. If determining the optimal K using BIC or AIC still feels like too much manual hyperparameter search, there is an ultimate upgrade: Bayesian Gaussian mixture models. The fundamental question this addresses is, what if the algorithm could find the optimal number of clusters for you, inherently determining the true dimensionality of the underlying structure? The solution lies in the Bayesian Gaussian mixture, class available in popular libraries. This sophisticated model can automatically determine the required number of clusters, removing the manual search process entirely. Here's how it works. You start by setting n components to a number that you believe is comfortably larger than the true number of clusters, say 10, as shown in the initial bar chart where all components start with equal weight. The algorithm then treats the component weights as parameters to be learned. If a component is deemed unnecessary or redundant for accurately fitting the data distribution, the algorithm drives the weight of that component effectively to 0, a process known as pruning. The result graph clearly shows that out of 10 initial components, only 2 or 3 retained significant weight, allowing the model to self-select the optimal, minimal structure required to explain the observed data. We've covered 3 powerful, yet fundamentally distinct, unsupervised clustering algorithms. This cheat sheet provides a rapid, high-level comparison across key dimensions to help you choose the right tool for the job. K-means is the general-purpose clustering workhorse. It handles spherical, similarly sized clusters with excellent linear scalability, making it the fastest choice for huge datasets. We determine K using simple, intuitive heuristics like the elbow and silhouette score. DBSCAN is your go-to when you need to find clusters of arbitrary, non-spherical shapes and when you need robust identification of noise or outliers. Its poor OM2 scalability limits it to smaller datasets, but its huge advantage is that it automatically discovers the number of clusters, eliminating the need to choose K. Finally, GMM, Gaussian mixture models, is ideal for ellipsoidal data. It offers soft clustering, density estimation, and requires more rigorous parameter selection. We select K using information criteria like BIC or AIC, or, for the ultimate automation, we use the Bayesian GMM variant, which finds K automatically. Always remember, your choice depends entirely on the inherent geometry and structure of your data. K-means, DBSCAN, and GMM are the primary algorithms, but the unsupervised toolbox is vast and continues to expand. Let's take a quick glimpse at 5 other important clustering methods, each designed to solve specific challenges or improve scalability. Agglomerative clustering is a hierarchical method that builds a tree structure, starting with every instance as its own cluster, and then iteratively merging the closest pairs until the desired hierarchy is complete. BIRCH, which stands for Balanced Iterative Reducing and Clustering Using Hierarchies, is specifically designed for very large datasets, using a highly efficient tree structure to be much faster than batch k-means on massive data streams. Mean shift is a sophisticated, density-based, non-parametric algorithm that shifts circles towards local density maxima to find cluster centers automatically, making it excellent when clusters have highly uneven densities. Spectral clustering uses advanced mathematics, specifically the eigenvalues of a similarity matrix, to project the data into a lower dimensional space where clusters are linearly separable, often excelling at finding complicated, non-convex shapes. And finally, affinity propagation is a novel approach where data instances vote for certain data points, called exemplars, to represent the clusters, automatically determining the number of clusters without requiring the user to specify k. Let's wrap up by returning to our foundational metaphor, the unsupervised cake. Unsupervised learning is truly the foundational cake of intelligence, providing the essential structure upon which all other machine learning models, supervised and reinforcement, are built. We have covered powerful tools that allow us to extract structure from data efficiently. We now possess methods for grouping through clustering, allowing us to segment customers or data, methods for finding oddities through anomaly detection using techniques like GMM density estimation, and methods for understanding distributions. The key takeaway is methodological. Always start simple with a robust workhorse like k-means, but critically, understand its limits. K-means assumes spheres, so if your data structure is complex, you must graduate to the right tool. Choose DBSCAN for arbitrary, complex shapes, or opt for GMM if you see ellipsoidal data or need probabilistic assignments and precise anomaly detection. The power of unsupervised learning lies in its ability to discover the latent structure in your data, and selecting the correct tool based on that inherent structure is the core of the challenge. Thank you for joining me on this deep dive into the Unsupervised Learning Playbook. We've mapped the foundational role of unsupervised methods, explored the elegance and efficiency of k-means, understood the power of density-based clustering with DBSCAN, and recognized the flexibility of probabilistic models like Gaussian mixture models. The ability to extract meaningful structure from raw, unlabeled data is increasingly critical in a world flooded with information, and mastering these techniques is essential for any modern data scientist. I hope this overview provides you with the clarity needed to select the correct algorithms and metrics for your next unsupervised project, whether it involves complex customer segmentation, image segmentation, or identifying critical anomalies in sensor data.